Good afternoon, everyone, and welcome to this digital conference. Today, I am happy to present a methodological contribution to the state-of-the-art of neural entrainment. The approach was originally motivated by my collaboration with Lousin Moumdijan, a colleague from IPAM who investigates auditory-motor coupling in patients with multiple sclerosis and cerebellar lesions. She stressed the need for introducing an outcome measure to quantify neural entrainment in her patient's population and hopefully orienting the development of musical neurofeedback applications in the future. Despite the fact that my colleague normally works with rehabilitation of gait behavior, we started simpler by developing the method on a dataset collected from 28 LT participants instructed to synchronize their finger tapping with a steady auditory metronome during 6 minutes and a half. In such condition of overt synchronization, we could validate the measure we propose by analyzing its correlations with a set of behavioral outcomes of accuracy and consistency of synchronization. In the state-of-the-art of neural entrainment, frequency tagging is a popular approach originally proposed by Nozaradan and colleagues in the context of perception and representation of musical rhythmic structures. It basically consists of identifying frequencies of interest in an auditory stimulus and quantifying the prominence of the same frequencies in the EEG spectrum via Fourier transform. In this simple example, you can see how individuals exposed to auditory stimulation containing a prominent periodic pulse or regular beat at a given frequency exhibit a dominant peak in the corresponding frequency bin of the EEG spectrum. The power of the Fourier coefficients has been extensively used to quantify neural entrainment. However, the measure does not explicitly account for the phase of the signal, arguably missing some information about the temporal dynamics underlying the process. Our stability index, on the other hand, is meant to be an outcome measure of neural entrainment explicitly based on the time-varying nature of the phenomenon. Now, the general idea is that entrainment is an active and dynamic process, and if the brain is actively engaged in tracking the beat, we would expect to identify a component in the signal which dynamically attunes to the stimulus by continuously slowing down and speeding up its oscillations in the process of achieving stable synchronization. The concept of frequency tagging was for us the starting point to develop the method we hereby propose. As a first step, we extracted from the EEG signal the component which was maximally entrained to an auditory metronome, given the metronome's frequency, hence the frequency tagging. Most importantly, once the component was extracted, we intended to quantify its frequency fluctuations over time. I will avoid going too much into the technicalities. For that, you can refer to our paper, which got recently published. And definitely ask me any question after this presentation. The real-time version of me will be more than happy to try to answer. The way we extracted the entrained component of interest was by means of generalized eigendecomposition. In short, the method allowed us to find the weighted combination of electrodes which best separated narrowband entrained activity from broadband intrinsic or endogenous activity. The purpose was to design a spatial filter to reduce the dimensionality of the data from our 64 channels to one single time series, which prevents electrode selection bias and is optimal for time course analysis at the level of long single trials. The quality of our source separation could be assessed according to three main criteria. What you're going to see is what you're seeing right now on screen. It represents the grand average of the whole sample of 28 participants. On the left, you can see the topographical activation map of the entrained component, which happens to exhibit maximal activation over left centroparietal scalp regions, suggesting possibly an important contribution of primary sensorimotor regions, given that participants were performing the task with the contralateral right hand. The plot in the middle represents the power spectrum expressed in signal-to-noise ratio units, percentage units, of the entrained component. And as you can see, according to the principles of frequency tagging, we would expect it to exhibit a very dominant peak exactly centered at the metronome frequency, which happened to be 1.65 hertz. Finally, among all the whole set of eigenvectors extracted via the decomposition, we selected the one associated with the highest eigenvalue. And the eigenspectrum that you see is particularly desirable. It's a good sign of the outcome of the source separation. Here you see graphically resumed the steps which lead to the computation of the stability index. As I mentioned, the starting point consists of the design of a spatial filter, which we use to compute the weighted average of the multivariate EEG dataset, extracting one single time series, which should be the maximally entrained component, as I said. After this, basically, we need to get from this time series to a time series of phase angles. In order to obtain a reliable phase angle time series, we need first of all to filter the entrained component. And for doing this, we used a narrowband Gaussian filter centered at the stimulation frequency. Then, via Hilbert transform, we computed the analytic signal, and from the analytic signal, we extracted the phase angles. Based, as I say, the stability index is a phase-based measure. Hence, based on the rate of change of the phase, we could compute a time series, a time-varying series of instantaneous frequency. So the concept, the idea is that over time, the component would speed up, hence accelerating, increasing the instantaneous frequency on a sample-by-sample basis, or slowing down, but always fluctuating around the expected stimulation frequency, which, as I said, in this case was 1.65 hertz. So in the ideal and absolutely unrealistic case of an entrained component in the brain perfectly oscillating all the time at the stimulation frequency, we would observe a flat line. But biologically, what happens is that the component would oscillate, trying to achieve a stable synchronization. Then, once you dispose of this time series, you can choose your time window of interest. In our case, we selected the whole session, 6 minutes, hence. And you can compute just the standard deviation of the instantaneous frequency. Hence, a standard deviation of 0, is stability index of 0, would imply perfect stable synchronization all the time with the stimulation, whereas broader fluctuations would result in a higher stability index. When looking at the correlations with behavior, you can see that concerning the accuracy, quantified by means of a relative phase angle of the tapping time series and the mean asynchrony with respect to the metronome expressed in millisecond, you can see that the stability index increases the less accurate the participants are in behaviorally synchronizing with the metronome. Concerning the consistency, quantified by means of the resultant vector length of the relative phase time series, the phase difference between the tapping and the metronome onsets, you can see the same pattern. We have, in the three cases, very significant but moderate correlation, negative correlations between the behavioral outcome measures and the stability index, meaning, again, broader fluctuations, more instability, less consistency in the behavior, and less accuracy. We did not find any significant correlation with the interbeat deviation, which is a measure of tempo accuracy, tempo matching, meaning how the tempo overall of the tapping time series and the metronome was similar. I would leave this open for discussion afterwards. We have some hypotheses about this finding. Then, getting to the conclusion, these are the following points that I would leave open for discussion. Is stability index actually a valid neural outcome measure of entrainment? By purely looking at the correlations, we suggest that there is some evidence for that, but again, I would like to know what you think about that. Is the stability index informative about actually brain mechanisms? Is the stability index actually tracking, is an index of the brain tracking the beat over time, and can we export it to new experimental paradigms? I have in mind some answers for that. I'd like to know your opinion, so I would leave it open for discussion. And with this, I'd like to thank you for your attention, and have a nice rest of the conference. Enjoy.